Chapter 7 will be about valuation and scenario analysis. It's a really terrible name. Practically, this will introduce us all the future pricing, forward pricing, and also option pricing building blocks, and also conditions. So how probabilities can be built in this system, and yes, so this terrible name can be distinguished in the following way by using the help of Mr. Jeremy Clarkson. So if you have to estimate the future cash flows, then we have two opportunities. First of all, we can focus on the expected values. So what can happen? So how can we estimate the present value of future cash flows? So practically what we did before in the C appendix. Or in the case of scenario analysis, we should see that what can happen at a defined level of probabilities. So in this case, we should find some kind of probability distribution. In the case of the book, it will be normal distribution. And also, I would like to show you that how can we deal with stable distributions to introduce also fat tailness. So practically with the two facial expressions that what can possibly go wrong and could be worse scenarios. So this one, scenario analysis, is much more about extreme outcomes, and practically we don't care about scenarios, we will care about probability distributions and thresholds like 5% probability or 1% probability in the future. So this side will introduce us value at risk and expected shortfall, and on the right side we will see valuation at the level of options, forwards, and stuff like this. So yeah. And this is where the ugly things are starting to appear. So first of all, we have the following setup. Continuous compounding will happen, luckily, because otherwise it would be completely ugly and disgusting. So that's why we are using this. We are using natural logarithm because we have this feature here. So if we have a threshold level, so we would like to explore what is happening if the spot price at the t time point will be smaller than a value v. So the probability of this event will be the same when we are taking all of them to logarithm. And it's much better for us because if we are taking everything to logarithm, then we know that everything will be reduced from to a more simplified mathematical expression. So what was before multiplication, now it's addition and so on. So we can make stuff easier, and also the exponential nature of the capital market will be removed. And asset pricing is S0 constant expected growth rate, which is, we know it's quite romantic, but still we have to have an expected growth rate, which we know that it's close to zero. So this is what we expect from the asset, and constant volatility, which we know that yeah, right now we should expect this one, but we know that even if it's not constant, then by using a gauge model and fitting it, we can create practically, or we can convert this model to what is the name? Conditional, to a conditional model. So for each day, if we are able to define the constant volatility, which is fitted well for that specific day, then we can convert everything to the level of t. But right now we are saying that okay, this can be assumed constant. Maybe this constant is just constant for a day. So, and we have the normal distribution. Why? Because this is the simplest way. Because we have just the expected value, we have the volatility, and we don't need any further parameters. If you are using stable distribution, It can be also parametricized, and there is a conversion back and forth. So if we are going to Matlab, not here. So if we are going to Matlab and we are saying that stable distribution, okay, this one looks disgusting, but if we are going down, then yeah, there is. So how can we link normal distribution to stable distributions? Practically, we have to set the alpha parameter which defines the tails of the distribution. We have to set the asymmetric settings to 0, so in this case it will be symmetric. And after that we can see that the last two parameters are familiar for us. So volatility can be modified, not the same. So here we had variance, and here we have standard deviation divided by the square root of 2. But the last parameter is familiar for us, so this is the expected value. So there is a way to move between back and forth between stable distributions and normal distributions. And after that, if someone would like to convert this one, then we can do it. Yeah. Okay, so why it's good for us? Because after that we can say that if you are taking the logarithm of this asset price in time t, then the expected value, so the mean of this, and the volatility, so the standard deviation of this, will be still parametricizing these things. And after that, we can say that, yeah, this is the probability distribution. So this is how we can calibrate normal distribution. So this is nothing new here, just we are describing the same thing with the data set in time t. Okay. If not clear, then still we can say let's Google normal distribution, and after that the first finding at Wikipedia will give us the proper equation. Because what can happen if we are saying that, so if this thing parametricizing the mean, this one is parametricizing the expected value, and we are taking also t to the equation, then but just taking critical values, so we have this unknown threshold v because we don't like this thing here, then we just have to say that, okay, we are inside normal distribution, so ln minus, ln v minus ln right now the spot rate, and minus these components divided by these variables. So this is how we can define that, okay, what is the probability of this one. So this is when we are talking about cumulative normal distribution function, and yeah, this is the density. So yeah, so this is the without any integrals. These things can be much more familiar for us. Just really some things to organize. So first of all, let's build these things up. So let's see that what is the probability of this and yeah, so everything which is here can be expressed in the following way, and this is also considered as a main building block, because if you remember on option pricing, they were always playing with D1 and D2. So once we are able to create a function which describes the D2, then it will be really easy for us to compute anything. So let's take our friendly. What happens? Yeah, so let's take our friendly Matlab here again, and let's see. Volatility surprises, so in this case we can find it later on. So probability of ST is smaller than V. It can be also sort of obvious that obviously if there is a difference between the logarithmic value of V and S, then if you are taking the logarithm out, then to make everything simplified, then this division, this distance will be a division. And yeah, this is all the mathematical trick here. So, and this is the D2. To make everything more reliable, so if we have any kind of major division in an equation, we are always starting with the division, and that's okay, take the point division. Practically it doesn't matter right now, but let's not forget to use this one, and already we should write in the brackets, because otherwise we can have a terrible day. Okay, and inside of this one there are already two different brackets. So this one and this one, and after that we can say that okay, but there is natural logarithm, and after that S0 divided by the threshold V, and here we have multiplication with T, and after that this is the mu, the expected value, minus another bracket sigma on squares, yeah, squares. I never prefer, so if we have one operator here, then okay, and divided by 2 sigma. So this one is in the bracket, this is in the bracket, this expression is also inside the bracket, and also this expression is also inside the bracket. So this is where we can make mistakes. Practically this would be completely the same in Excel, just in this case we should have no sigma and so on, just the cell numbers. So if you would copy and paste it into Excel, it would be the same. Okay, and here we have sigma multiplied by sqrt square root of b. Where does this come from? From here. So, and especially here. So this is coming from the variance. So after we organize everything nicely going through the math, then we have this expression here, because before we had yeah, the comma, and to remove the comma we have to reorganize everything. Okay, so after that, let's see that what kind of inputs do we need here. We already have the spot rate. Let's copy everything back again, because it's more elegant to see it. And also we have the mu, which is 0. We have the sigma, which is, let's say, 0.01, so it's only 1% of so this is volatility, risk, and so on. Okay. Yeah, and this is the threshold, so we should introduce a threshold here. So spot rate is this one, so let's say 80 is the threshold. Then I think what is the name of natural logarithm in Matlab? Oh, just a simple log. Okay, because log is always not the natural logarithm in Excel, because yeah, this is the significant difference between Matlab and Excel. But here we can see that, okay, this is what is happening. So this one is a very small number, this one is quite a big one. Obviously, if we are adding them together, then it will be still a positive. So obviously what matters for us that if we start to increase the sigma, then the sigma is on squares. So its importance will start to shrink away. How can we see this? Maybe let's write a 4 cycle on this. 4 sigma 1 till 100, and that's right now I cannot divide it with 100, so not this way. 4 5 till 100. Thank you. So I divide it by 100, and so once we are able to increase this one, this d value starts to shrink away. So this one is not so responsive, or it's responsive, but also what we can see that this process is absolutely nonlinear. So there is this curvy part, so at the beginning it always looks like it's linear, then it arrives here, and after that, after 20 maybe we could say that we can fit a linear function on this. So that's why if you can find anywhere this kind of function here, then non-linearities will always happen to us. So it will be a meaningful feature. And of course we can say that, okay, the probability of being bigger than the threshold will be utterly the same. So yeah, still we are not computing this one. So okay, that was just my pet project here to show us. Because right now this is just D, but now we can say that. So okay, and right now this is the normal distribution. So we just should put data inside the normal distribution, and in this case we need CDF, cumulative distribution function. I cannot. I already opened this one. Not ICDF, but CDF. Obviously we have a general. So we could have normal distribution, just in this case I would like to generalize as much as possible. So you can see here that if we are taking I. Why it's I? CDF values. Yeah, just this is probability, so relative normal distribution. Yes, it's probability. So okay, the name. Name. In this case, let's use normal right now. So we don't want to have any kind of fancy first. And in this case, we just have to parameterize. A will be the mean. So this is the mu. And B will be sigma. If we are using different distributions, then we just have to change the name here, and also we have to add this kind of parameters. So if we need a third parameter, then just we are adding a comma and typing it here, so it's behaving in a nice way. And the x will be minus d2. So hopefully, oh, it provided everything. Why? Yeah, oh, yeah, because I am build up the D2 as a vector, sorry. Yeah. Whole experiment. Yeah, I did not change this one back. So sigma is a now a finite number. Yes, and also removing the force cycle from here. After executing my script, which was perfectly fine until I put force cycle in it, Man, why 0? Why? Why are you doing this? This is supposed to be values to which evaluate CDF. Yes, we evaluated the CDF. Why you don't like me? Minus D2, yeah, supposed to. It says it's impossible. Let's say that am I using the appropriate function or not, so cumulative normal distribution function. Yes, we should fit it to the data. Yeah, norm CDF. This is what I'm talking about. Okay, everybody says it's 0. So 90. Oh, I should not have sigma. Sigma. Yeah, we have two sigmas. Just yeah, this happened a year ago as well. So this sigma is not that sigma because this is coming from the data and this is coming from the theoretical distribution of the data. So yeah, it's 1. So right now we should have a standard normal distribution function. And I think that in this case, yes, we have a probability. Because in this case, if I'm defining the data-related sigma, then it will be so narrow that practically it's not fluctuating at all. So it's a normal distribution like my hand. So it's and poor thing has no chance to fluctuate at all. In this case, it has. Okay, and now we can see that. We have the probability. So never forget this. If we would, no, we would not. Yeah, and after that we can have the expected payoff. Well, let's not provide any kind of fancy letters here, so let's say that just P multiplying the payment. Here, so what is the payment in this case? Yeah, so if we are paid in a situation where we have the threshold and we have to be under it, then it will be the difference between them. So B minus S0. And it will be a sad negative number. Okay, and what is happening if the probability is bigger? Oh, let's put this one here, and in this case it will be much more visible. then the situation is completely the same, just we are in the opposite direction, so that's why the D2 is not minus anymore, so we are on the other end, and now we get 10 money. So yeah. So practically at the end of the day, it says that Q probability of ST will be smaller and bigger than the threshold. It will be Q. So it says after that the V will be described. So this threshold of probability will be described in this way. So it is just reorganizing the same expression. Now we can use it for things. It's so good that it's able to. Okay. Just not click on it. So good that it's able to import these special characters as well. Other Matlabs were not able to do that. And now we can see that, okay, but before it was normal distribution, now it's the inverse. Because we are moving out from this kind of expression, so it was a lot of rows under each other in the book until it was able to reach to this conclusion that if we would like to take the V out from this expression, then this reorganization is necessary. So yeah, it was not just immediate that it's coming from the sky, just yeah. Okay, so in this case, V will be equal to all these things together. So S0 multiplies EXP, and then many things here. First bracket, which is multiplied by t, then plus, and of course it can be minus by the inverse. Luckily, CDF and ICDF functions are completely the same, just we have different setups. And since we moved, instead of defining the probability, right now we have a set predefined probability here as the threshold probability, so we can say that I don't know why it's Q probability, why it's not just P probability, but okay, so 0.05, 5%. And still have this thing here, which is multiplying the normal distribution. Oh, and we should start here as well. So this mu, sigma, and so on thingy can be copied here and here as well. Let's say that minus, yes, sigma is on square divided by 2 and multiplied by t. So if we have this, okay, my usual bracket we have excessive. Yeah, this bracket is excessive. Okay, this one now it's closed. And this one's supposed to close somewhere. Yeah, okay, now it's closed here. Let's try again. And this one is... So if you would like to have this set up that, okay, what is the probability of being over or under the threshold value? Sorry, we know the probability, so, but what will be the threshold value if we are saying that there can be 5% chance of movement, then we can see that, okay, these are the thresholds. That's the upper threshold and this is the lower threshold. Under this circumstance here. How can we make this more funnier? Obviously, if we are saying that, yeah, it's so for normal distributions. And for stable, I mean, in the case of stable, we are not talking about the building where the horses are living, but we are talking about this guy here. So first let's build up the normal like setup, and after that we start to torture this one to see that what will happen. Okay, so calibration. Yeah, we can keep this one here because in this case we can see the setup, and otherwise we can have the parameters here. So yeah, copying, and now instead of normal it will be stable. And after that we have 4 different parameters. So it's this one, and after that let's just say that, okay, or should we say that let's give alpha beta, because in this case I can highlight the importance of A, B, C, D. So this is the expected value, like mu in normal distribution. So this can be 0. The C is not on square anymore, but we have to take, yeah, so before of that it was just a standard normal distribution, so it doesn't matter that one is on squares or not on squares, because yeah, it's the same. But now we should take 1 divided by the square root of SQRT 2. And after that, the B is the skewness or asymmetry. So it can be 0, or it can be minus or negative number, or positive number. And this is the 2. If it's set to 2, then, sorry, this is the tail parameter. And what I'm writing here? And if we are going up, it says first shape parameter, so it can be anywhere between 0 and 2, but practically so it says that please don't be near 0, because in this case it can create strange behavior, so mostly 1. Okay, but if you are having this setup, then it should provide us the same results. So let's copy it here. Yep. So as you can see, it's working. We built something which is working, so I'm proud of it. So this is the stable V, and this is the normal distribution V. If we are doing the same thing, we can say that this still works. So after that, let's start the torture. So let's say that yeah, let's go back to the positive threshold. So we should be around 98. And what happens if we have longer tails? So instead of 2, let's say 1, because the model says that it will work well. So, and now we can see that the threshold value can be smaller. So practically, if we are setting the same probability with fat tailness, then it allows us more movement. So before of that, it said that it will be end sooner, but now it's not. So what happens if we are saying it's 0.5? It still should be allowed. It's even lower. But this is not a linear behavior. So before of that it was 95 after halving it, and now it's 67. So it's jumping a lot. So this is also the problem of fat tailness, that if you just start to allow it, then yep, we will start to have a bad day. Okay, let's go back to the initial 2 value, and then let's see what is happening with asymmetry if we are adding to the game. So minus 0.5. So the initial value was 98, so yeah. It is skewed in one direction. Maybe it was too aggressive from me, because now it says that it's... oh, I should highlight everything and run again. Yeah, so it has just a minor influence until no fat tailness was added. If fat tailness was added, we will be able to see that it was also extended further. So -2. Maybe I'm in the wrong direction right now, because I'm in the positive side, so I should... Skewness doesn't matter right now. Okay, for some reasons it's completely robust on this one, so. But at least fat tailness was introduced that way. So we can extend this further. So it's not just for normal distributions, as the book says, but also we can add funny things here, because it doesn't matter that at least this part of the equation is separated from the rest. Still, we could say that but it's not elegant because we are using mu and sigma because it was a building core of the normal distribution. So it's not nice, but it's functional. So. Because we are coming from this way. So yeah, okay. Then